Okay, this is lesson 10.5, the distance formula. We can find the distance between 2 points on the coordinate plane by drawing a right triangle and using Pythagorean theorem. The distance formula, which is based on the Pythagorean theorem, can also be used to find the distance between 2 points on the coordinate plane. And this figure here goes with this information here to show you what the distance formula is. So if you have 2 points on the coordinate plane that have coordinates x1, y1, and x2, y2, this formula here will give us the distance between those 2 points. Now, this looks like a pretty messy formula. We've got some subtraction, some squaring, some adding, a big old square root. So with this formula, it's going to be very important that we do these in parts and not try to do the whole thing all at once. But I find that it's actually easier to understand this formula if you see how it comes from Pythagorean theorem. So what we're going to do for this first part is to see how both methods can be used to find the distance between these 2 points. And then when we're done, we'll take a look at the similarities between those two methods so that you can really see, again, where that distance formula comes from. So on our graph, let's go ahead and plot the points 5, -6, and 1, 2. And we'll want to draw a nice straight line between them. Alright, now in order to use Pythagorean theorem, we need to have a right triangle. So, similar to how we calculated slope, where we calculated rise and then run, we're going to draw in that right triangle. So, we'll go straight down, and then straight across. So now what we have is a right angle right here, and we have the hypotenuse of the triangle that we're trying to find. Well, we can count distances horizontally and vertically on the coordinate plane. So this is 1, 2, 3, 4 units, and this is 1, 2, 3, 4, 5, 6, 7, 8 units. And this is the side that we are looking for. So using Pythagorean theorem, a squared plus b squared equals c squared. Remember that these two sides are the legs. Those are a and b. It doesn't matter which one's which. So let's call the a 4 and the b 8. And then 4 squared is 16. 8 squared is 64. When we add these together, we get 80. And then we don't want c squared, we just want c, so we'll take the square root of both of these. And don't forget, when you do that, there are two solutions to this, so plus or minus. And the square root of 80 to the nearest tenth is approximately 8.9. But since we're talking about distance, we know distance can't be negative, so we'll only take the positive solution of the two solutions here. So this will be just 8.9. Okay. So that's using Pythagorean theorem. Obviously, in order to use that, you would have to have a graph and actually be able to draw the right triangle. So let's take a look at the distance formula. This one, we're going to plug in the coordinates of the points. So the first thing we want to do is label these points with the coordinates. So this is x1 and y1 and x2, y2. So the distance formula says d is equal to the square root of x2 minus x1 squared plus y2 minus y1 squared. And that's just copying down the formula. So now let's put the numbers into the formula where they belong. Okay. x2 is 1 minus x1, which is 5. And then y2 is 2 minus y1, which is negative 6. Okay. Alright, so now, like I said, we're going to want to do this a few steps at a time, because if you try to type this whole thing in your calculator at once, the chances of missing something or forgetting parentheses somewhere or something like that are way too high. So let's go ahead and use our just good old order of operations, and we'll do what's in the parentheses here first. So 1 minus 5 is negative 4. And then 2 minus negative 6, that's like 2 plus 6. That's 8. And now that we've done the parentheses, we can take care of exponents. Negative 4 squared is 16. Make sure if you put this in the calculator that you put parentheses around that negative 4. If you type in negative 4 squared, it will tell you it's negative 16, and it is not negative 16. 8 squared is 64. So now we'll add. We get the square root of 80, and then we take the square root, and we get about 8.9. Hey, look, same answer. So again, let's take a look at the distance formula and see how it's similar to Pythagorean theorem so we can see where this comes from so it's not just this nonsense formula. Well, here's where they start to look similar. We have square root of 80, square root of 80. Where did the 80 come from? Well, 16 and 64. 16 and 64. Where did those numbers come from? Well, here it was negative 4 squared and 8 squared. Here we had 4 squared and 8 squared. But that really is just because when we counted distance here, we knew that it couldn't be negative, so we just counted from left to right. And then we counted here from top to bottom. Here, when you subtract these, they will have signs on them, but when you square them, you get the same numbers. So if we had had 4 squared, we got 16. Here we had negative 4 squared, we got 16. So that takes care of that negative. So then the question is really, how did we end up with 4 and 8 from these? Well, the distance from x1 to x2, from the first x-coordinate to the second x-coordinate, is just this horizontal distance, which is 4. That's where that 4 came from. The vertical distance from y1 to y2 is the difference between that vertical distance, and that's where we came up with 8. So really, the distance formula is just Pythagorean theorem in disguise. Now, this might look a lot messier than this was, so why on earth would we use the distance formula when we could just use Pythagorean theorem? Well, 2 reasons, really. Pythagorean theorem, you will always have to have graph paper, and you will have to plot the points and draw the triangle every time in order to use Pythagorean theorem. So that's obviously one benefit that the distance formula has, is that you can use the distance formula anytime. You don't have to have graph paper, you don't have to draw the graph and plot the points. The other thing to keep in mind is, what if you had some numbers that were not as nice as these numbers that we had? Let's say you had coordinates that were fractions or decimals, or let's say that you maybe had coordinates that were really, really large numbers. You wouldn't want to have to draw a graph that was that big for large numbers, and you certainly wouldn't be able to count spaces on the graph very easily if they were fractions or decimals. So the distance formula obviously has some advantages that Pythagorean theorem does not. Now most of the problems we will work with will be small, manageable numbers, but still you want to get practice with the distance formula since it's something new, and because it's a little bit better to use than Pythagorean theorem. So for the rest of the problems we will use the distance formula instead of Pythagorean theorem. So example 1 says, use the distance formula to find the distance between 8, 4 and negative 6, negative 2. Round to the nearest tenth if necessary. Okay, so in the formula, remember the first thing we need is to label the points so that we make sure the right numbers go in the right places. So this is x1, y1, x2, y2. Okay, so in the formula, starts off with d equals the square root of, and this is x2 minus x1. So x2 is negative 6 minus x1, which is 8, squared. And then plus y2 minus y1, negative 2 minus 4, squared. Remember to do this in multiple steps so that we don't accidentally miss something. So take care of the parentheses first. Negative 6 minus 8 is negative 14. Negative 2 minus 4 is negative 6. Alright, now that we've taken care of parentheses, let's do the exponents. Remember, you have to have parentheses around these before you put them in the calculator. So negative 14 squared is 196. Negative 6 squared is 36. Now we'll add, and you should get 232. And lastly, we'll take the square root of 232, and we'll get that this is approximately 15.2. Okay. For the try it yourself problem, you're going to do the same thing. Make sure you're using the distance formula. So make sure you label your points, plug them in the right places, and then, again, follow each of those steps so that you're not going to miss something trying to skip a step. So pause the video, work through that problem. When you're ready to check your answer, press play. Okay, for this one, you should have gotten that the distance is equal to approximately 10.2. Okay, let's go on to the next page. Knowing the coordinates of points on a figure allows you to draw conclusions and solve problems about the figure on the coordinate plane. So, for example 2, we want to classify a triangle TUV with vertices T at negative 2, 8, U at negative 3, 1, and V at 3, 3 by its sides. So we want to classify the triangle by its sides. Then find its perimeter to the nearest 10th. Okay, so let's go ahead and use this graph to plot those 3 points to see what the triangle looks like. So we'll point at negative 2, 8. We'll point at negative 3, 1. And a point at 3, 3. Alright, and we will connect those with straight lines. To make the triangle. And let's go ahead and also label these with the letters. T was at negative 2, 8, so this is T. U at negative 3, 1, this is point U. And then 3, 3 is point B. Okay. Well, we talked about how to classify triangles in section 10.3. So to classify by its sides, we would need to know how many of these sides have the same length. Well, looking at this picture, I really can't tell. These look like some of them might be close to the same length. It could be isosceles, it could be equilateral, or who knows, these might be really not exactly the same, but just really close, enough that they look like it, but we can't really tell. So we could possibly have a scalene triangle. Not knowing, we would have to know the actual lengths of those sides in order to actually be able to make that conclusion. So that's what we're going to do. We're going to use the distance formula to find the lengths of each of those sides. So because those are 3 different segments, we're going to have to use the distance formula 3 times. Alright, so let's go one segment at a time. Let's find the length of TU. So we're going from point T at negative 2, 8 to point U at negative 3, 1. Alright, so let's go ahead and label our points. X1, Y1, and X2, Y2. And let's use the distance formula to find the length of that segment. So remember the formula is X2 minus X1, so negative 3 minus negative 2 squared. And make sure that you get the minus from the formula and the negative from this number. Plus y2 minus y1, 1 minus 8 squared. Alright, take care of the parentheses. Negative 3 minus negative 2, that's like negative 3 plus 2, that's negative 1. And then 1 minus 8 is negative 7. Let's square each of those, so we'll get 1 plus 49. So that gives us the square root of 50, or to the nearest tenth, that is approximately 7.1. Okay, so we know the distance from point T to point U is about 7.1. Alright, let's go to the next segment. Now let's find the distance from T to V. So from point T at negative 2, 8 to point V at 3, 3. And once again, we'll label our points x1, y1, and x2, y2. Alright, and we'll stick those in the distance formula. So x2 minus x1, 3 minus negative 2, squared, plus y2 minus y1, 3 minus 8, squared. Okay. And then we'll take care of the parentheses. So this is 3 plus 2, so that's 5 squared. And then 3 minus 8 is negative 5 squared. Square each of those to get 25 plus 25. And when we add those together, that is 50. And the square root of 50, once again, same thing, is 7.1 approximately. So this side is also 7.1. So we know now we at least have an isosceles triangle. Depending on the length of this segment, it may even be equilateral. But we know for sure that it's isosceles. Let's go ahead and find the length of the last segment. So now we need the length from U to V. So UV. U is at negative 3, 1. And V is at 3, 3. So we'll label those x1, y1, x2, y2, and now the formula. Alright, so we have x2 minus x1, 3 minus negative 3, squared, plus y2 minus y1, 3 minus 1, squared. Three minus negative 3, it's like 3 plus 3, so that's 6 squared. And then 3 minus 1 is 2, so it's 2 squared. Square both numbers, that gives us 36 plus 4, which is 40. And then to the nearest tenth, the square root of 40 is 6.3. So this side is 6.3. Okay, so now we can classify the triangle by its sides. We see two sides with the same length and a third side with a different length. So this is a, sorry, not a scalene triangle, an isosceles triangle. Okay, once we've done that, we want to find its perimeter. Well, the perimeter is just the three sides added together. So 7.1 plus 7.1 plus 6.3. When we add those together, we get 20.5. The triangle is isosceles with a perimeter of 20.5. Okay. There's a try-it-yourself problem that is very similar to this one. So go ahead and pause the video, and as you can see from that example, these problems will take a little bit of time to complete because you do have to use the distance formula 3 times. So go ahead and pause the video, work through that problem, and when you're completely finished and you're ready to check your answers, go ahead and press play to continue. Okay, so here's your triangle. If you graphed it, this is what it should have looked like. Oops, I forgot to label point C. Alright, for the lengths of each side, from A to B is 7.1. From B to C is 8.1, and from A to C is 9.2. So that would make this a scalene triangle, since none of the sides are the same, and the perimeter is 24.4. Okay, let's continue to section 10.6, special right triangles. And we'll talk about two different special right triangles in this section. In class, we'll talk about what makes these so special, but for right now, we just want to figure out how we can use these special relationships and these special right triangles to solve some problems. So the first one, a 45-degree, 45-degree, 90-degree triangle, is a special right triangle whose angles measure, go figure, 45 degrees, and 90 degrees, creating a right isosceles triangle. Since the two angles are the same, the two sides are also the same. All 45, 45, 90 triangles are similar. They have corresponding congruent angles and proportional side lengths. And because they're all similar, and because they have those proportional side lengths, we can use that to solve problems where you only know one or two of those sides. So you have this picture here that shows a 45, 45, 90 triangle. And in words, this says in a 45, 45, 90 triangle, the length of the hypotenuse is the square root of 2 times the length of a leg. So if you knew the length of one of the legs, you would just multiply it by the square root of 2 to get the length of the hypotenuse. And that's true for any 45, 45, 90 right triangle. It doesn't matter what the length of the leg is, the hypotenuse is that number times the square root of 2. So let's see how we can use that to solve some problems. Example 1 says to find the length of each hypotenuse. So in this one, the way I like to solve these special right triangle problems is to first identify, because sometimes the triangle is turned very, very strangely. First identify which sides you have. So here, because we know it's a 45, 45, 90 triangle, 45, 45, 90, we know our two legs are A and A. So the two legs here are A and A. And then the hypotenuse is A square root of 2. Okay, once you've labeled it, look at one of the sides that you actually have the length of. Here we know that the length of this leg is 3. So that tells me that A is equal to 3. Well, if A is equal to 3, then this is equal to 3 square root of 2. Or 3 times the square root of 2. Let's do the same thing for B. It's a 45, 45, 90 triangle. So the two legs are going to be labeled A, and the hypotenuse is A square root of 2. So once again, let's take a look at one of the sides we know. That tells me that A is 17. So we can replace A here with 17, and we'll have that X is equal to 17 square root of 2. Alright, so go ahead and try the two try-it-yourself problems at the bottom of this page. Pause the video and work through those two. When you're ready to check your answers, press play to continue. Okay, the hypotenuse for the first one is 6 square root of 2. And for the second one, it's 15 square root of 2. Alright, let's go ahead and continue and talk about the other special right triangle. So another special right triangle is a 30-degree, 60-degree, 90-degree triangle. Just as all 45, 45, 90 triangles are similar, all 30, 60, 90 triangles are similar. They have corresponding congruent angles and proportional sides. So here's our model. Now this is a little bit more difficult than the 45, 45, 90, but we'll still approach these problems the same way. So in a 30, 60, 90 triangle, the length of the hypotenuse is 2 times the length of the shorter leg. So here's the shorter leg, which is A, and here's the hypotenuse, which is 2A. The length of the longer leg is square root of 3 times the length of the shorter leg. So here's the short leg, A, and here's the long leg, A times the square root of 3. So in symbols, hypotenuse is 2 times the shorter leg, longer leg is square root of 3 times the shorter leg. Okay. So let's see how we can approach these very similarly to how we approached 45, 45, 90 triangles. Alright, so the example here says to find the length of each missing measure. Okay. So here, before we even worry about which one we're missing, which ones we have the length of, let's go ahead and label the triangles just like we did with the 45, 45, 90s. So here we have to be a little more careful though, because we have 3 different side lengths. So the shortest leg is the one that's across from the 30-degree angle. So here's the 30-degree angle, here's the shortest leg. We will label that A. Well, if that's the short leg, the other one has to be the long leg, so we'll label that A square root of 3. So that leaves the hypotenuse, which we will label as 2A. Okay, so now let's find a length that we have. Here we have that the A is 4. And you could double check over here. If I replace this with 4, I get 4 square root of 3. That looks pretty good. So now here, if I replace the A with 4, I will get that x is equal to 2 times 4, or 8. Alright, let's do the same thing for B. So again, let's label our sides. So across from the 30-degree angle is the short side, which we label as A. The other leg is the longer leg, which is A square root of 3. And then the hypotenuse is 2A. Okay, here we don't have either of these lengths, but we do have this one. Now this tells me what 2A is equal to, and that's not really useful. I actually want to know what A is equal to. And you might be able to do this, hopefully, you'll be able to do this in your head. If 2A is 12, then A would obviously be 6. But if for some reason, maybe the numbers just look a little funny, maybe it doesn't quite jump out at you right away, we can just set up a quick equation to solve that. If 2A is 12, then A would have to equal 6. Alright, now let's replace A with 6 on the other sides. So this would be 6, and this A would be 6. Now we can see very easily that x is equal to A, which is 6, and y is equal to A square root of 3, and when we replace A with 6, that's 6 square root of 3. Okay. So for the try-it-yourself problems, you're going to pause the video, work through those, and when you're ready to check your answers, press play. Okay, for the first one, you get x as 17 square root of 3. And for the second one, x is 10, and y is 20.